Okay, let's go ahead and get going. So as always, first, let's start off by me just thanking everybody for taking a little bit of time out of your Wednesday afternoon to hear about some fun science going on with Green Bank Observatory. So I'm Karen O'Neill. I'm the director here at Green Bank Observatory. So we'll start off with me just giving you a little bit of news about what's going on the site, and then that'll be followed by our own Dave Frere, who's going to be talking about GBT observations of gas and some luminous IR galaxies. So what's going on around Green Bank? Of course, COVID is always something we think about. Number of vaccinations within the state of West Virginia, within the county, continues to creep up at a very, very slow rate, but at least it is continuing to go up a little bit. Number of cases has gone down over the last few days here within the county, and you can see that trend across all of West Virginia, the state that we're located in, down here in the bottom left of your screen, where you can see we've surpassed our peak and hopefully are on a downward swing. Fingers crossed that will continue all the way down as people continue to get vaccinated more and more over the next few months. So on site, of course, we're fully back to work. I've mentioned that a number of times. So we remain in full operations. The Science Center is open and visitors are coming back to site. All of that is fantastic for us. Other exciting news, we've got the new data center under construction. So this is a picture from about a week ago. What you can see on the inside here is the RFI shielded enclosure, which will enclose the data center. And then surrounding it is a building that's purely there for weather protection. So that will allow the shielded facility to last for much longer than it would without that. So that's all in place, and the shielded room is now fully complete. And we're going to begin work on finishing up the electrical components and putting the outside on that, with the intent that the data center should be fully usable by early next summer. Other work going on right now is grout replacement of the GBT track. This is something we've had to do on a regular occasion as the GBT ages. So the grout itself, if you can see this picture down here, the grout is this little bit right above the concrete formation that holds up the track and keeps it stable. As tends to happen as things age, the grout itself has aged. We've replaced 2 sections of grout over the GBT's lifetime, and we're actually doing 5 sections over the next 2 weeks. So these are just, again, preventative maintenance to try to make sure that our track itself is held stable and keeping the steel nice and straight so that our pointing on the GBT is fantastic. So again, that'll be going on for about 2 weeks. We've got a whole slew of other infrastructure projects that are taking advantage of the fact that the telescope will be shut down through the end of the month. And so we've got cable wraps going on and testing our prime focus feeds and refrigerators and all sorts of other things that are typically difficult to get done because we aren't shut down for this long period of time. So lots of maintenance, lots of things going on site. Other exciting news is the new calibration vane for our Argus. This is our 16 pixel W-band receiver that has been built and it's being tested in the lab right now. So assuming those tests are successful, so far they have been, this will go up onto the GBT by the end of the month. We'll have the new calibration vane for the high frequency season this year. So that's great. That's accounted for a decent amount of the downtime for Argus. And we're looking forward to this being up and Argus having a fantastic winter this year. So other things going on, we still have a number of job openings here on site. Some of them are getting filled. We're certainly getting some great applications in there, but if you know of anybody interested in coming to work for Green Bank Observatory, we're a great place to be. Then we strongly encourage you to have them take a look at our career page or take a look yourself and apply for some of the jobs. So what's coming up? We've got our community Zooms continuing. And so in the next community Zoom will be Amanda Kepley from the National Radio Astronomy Observatory. And then in early November, we have DJ Pisano, who's currently at West Virginia University talking to us. With that, the last thing I just want to say is this is the last time, most likely, that I'll be introducing the community Zoom. I'm stepping down as director, as you heard a few weeks ago, and Dr. Jim Jackson will be taking over on Monday. So thank you guys all very much for listening in on these. The community Zooms will continue and Jim Jackson will take over. So with that, I will hand it off to Jay to introduce today's speaker. Thank you.
Thanks very much, Karen. Yeah, today's speaker is Dave Frere. Excuse me, Dave Frere. Dave, why don't you put your first slide up and get going when you're ready. And I'd just like to remind everyone, if you have questions for Dave, please submit them through the Q&A box in the lower right hand of your screen, and we'll gather them and he can answer those at the end of his talk. Thanks very much.
Thanks, Jay. I'm a scientist here at the Green Bank Observatory, and when Jay asked me to give a presentation about a month ago, I purposely gave them a very vague title, GBT Observations of Gas and Luminous Infrared Galaxies. I could go with 3 or 4 different talks, but what I decided to talk about is our local universe, luminous infrared galaxies, and our GBT H1 observations of the gold sample. Oops, there. Okay, very quick outline. Before I jump into what the goals H1 survey, I want to note a few ongoing GBT surveys, large surveys that are currently ongoing. Then I'll give a little bit of my background motivation for studying LIRGs. We actually have 3 current large extragalactic surveys with the GBT. There's an H1 project doing 2,000 galaxies. There's a dense gas project that Amanda will talk about next week. Those observations are completed, but that data analysis is still ongoing. And then we have a new one to do 12 CO in nearby galaxies led by Alberto Bellato, and that's be starting up this semester. That's using Argus. And by the way, the Argus main tested just fine in the lab, and I think it's physically on the telescope right now. So we're putting it up today. So my motivation for studying LIRGs went back, my path to studying LIRGs in the local universe started at actually high redshift. And I'm not going to spend a lot of time here. It's just so I did research with the 140 foot and in the construction of the telescope, the GBT. So all this was done pre-GBT before we actually had the telescopes in place to study the high redshift universe. But what we've done with the GBT, so this is just a plug for GBT High Z science, we have followed up a lot of Herschel and Planck infrared sources, detected sources on the GBT with CO1 to 0 with the Herschel Atlas, H Atlas, as well as the Planck sample that Kevin Harrington had led. Basically, they're detected by Planck. They got the CO3 to 2 redshifts with the LMT. We've been following them up with the GBT 1 to 0. The GBT 1 to 0 is yellow versus the 3 to 2, which is orange here. If you just look, there's a lot of different range and ratios there, and it highlights the importance of getting 1 to 0 observations and why centimeter observations are important for understanding molecular gas in the early universe. Just a really little side note. People used to know this, but I'm not sure if everybody understands this now. We study CO at higher redshift because they're much brighter than trying to measure H1 gas at high redshift. H1 emission line is pretty weak. And the advantage of CO is you can actually climb up the molecular ladder as you go to higher redshifts such that it flattens out the intensity as you go to higher redshifts. So you can see CO at very high redshift where it'd be almost impossible to see H1 from an individual source. Okay, I'm going to go ahead and jump into the goals survey and what I plan to concentrate on today. So these are GBT observations. I actually done a decade ago, a little bit embarrassing, but I came here and then I got distracted following up the Herschel sources. This project has been worked on by students and postdocs over the last few years, but it's finally coming together. I went back and redid and the reduction in a very uniform way to get the data together for a paper. So the goal sample itself, it stands for the Great Observatories All Sky LIRG Survey. So it started out with the Spitzer project, really, but it has follow-up HST, Chandra, and Galaxy observations. And basically, after I came here in 2009, I was working with some of the goals team, and I decided, well, we might as well just do it with the GBT and do H1 observations. That's pretty simple to do. So what we targeted were out of the 203 goal sample sources, which are all the bright IRAS infrared galaxies from the All Sky survey. We selected all of them, 162 that were above 35 degrees, minus 35 degrees declination. We spent about 180 hours, and the bright sources I didn't spend much time on, 30 minutes, which are pretty deep. And so the fainter sources I'd spend, up to about 3 hours. And the thing to point out, or in just general, that there was single dish, big beam, even though with a very big beam, the GBT, our spatial resolution is only 9 arc minutes. So we're making global measurements here, which is powerful in another way because you see everything. So infrared galaxies, they were discovered in the 80s by the IRAS mission. It's very exciting because it's a new class of galaxies that were basically 2 orders of magnitude more luminous in the infrared than the typical spiral galaxies. And the LIRGs and ULIRG definition, ULIRGs just stands for ultraluminous. It's greater than 10 to the 12th solar luminosities, where LIRGs are greater than 10 to the 11th solar luminosities, where most regular galaxies are of order 10 to the 10th solar luminosities. They're associated with galaxy mergers and interactions in the local universe, and they're powered by extremely luminous starburst and AGN. And although they're relatively rare in the local universe, their numbers increase dramatically at high redshift, such that they significantly contribute to the total star formation across entire cosmic time. And there have been scores of papers written over the last 20 years from the Spitzer and Herschel missions highlighting the importance of understanding infrared luminous galaxies throughout the history of the universe. Here's some pretty pictures from HST, just showing some example images over a range of infrared luminosities. The lower luminosity is upper left to the higher luminosity is the lower right. It just highlights the fact that they're merger systems, and as they evolve to be in a more late stage merger, they tend to be more compact and more luminous. Whoops, down here. And this is just some simulations I pulled off the internet, just showing how how galaxies merge. You can have 2 interacting spirals, and then basically the gas and all the activity eventually falls into the central regions. And we know the molecular gas is driven in the central regions because we see that with the CO observations. But one could, there is still an open question: what happens to the neutral gas reservoir during the merger event? And just to give a little bit of background before I actually show the data from the GBT of the gold sample, just so people understand for some general context, normal spiral galaxies, H1 profiles are relatively flat with the radius. They go out to very high radius. In fact, this is the original case for arguing for dark matter, where CO tends to be centrally concentrated in the cores of the galaxies. And roughly speaking, the total mass in a molecular gas and H1 are fairly comparable in local spiral galaxies. Here's some pretty pictures if you looked at spiral galaxies in H1. This is from the THINGS sample. The thing I wanted to point out here, in a lot of the sources you see in the central regions, it's deficient in H1. Basically, all the gas in the center regions are basically molecular, where the CO is extended over large radii. And if you look at comparison of what people do, of course, is star formation rate versus gas, and you try to come up with some Kennecat law. It's been well known that the molecular gas correlates fairly well with star formation rate. Amanda could make the case next week that dense gas correlates even better than CO. But H1 is not correlated at all with star formation rate directly. And then if you look at this, this is basically star formation surface density versus gas surface density. And you don't see any H1 at high gas surface density. And that's because the H1 at high gas surface density becomes molecular. And there's just this critical transition, basically, when you get above about 10 solar masses per parsec squared, all H1 starts being converted into H2. This is relatively, well, not necessarily well understood, but well known, and there are models out there that argue this critical density is consistent with what we see in nearby spiral galaxies of order, when you get above 10 solar masses per parsec squared. So here's just the spectra of some of the galaxies in our sample. We have good data of 161 out of 162. There's still a little bit of work I need to do on one source. That's 3C84, which is a very bright continuum source, which makes the baselines more challenging. But anyway, the GBT data shows a wide variety of H1 profiles, ranging from the double horn profiles you see in spiral galaxies to multiple components, to absorption features, and then combination of emission and absorption features. And in terms of Diana was my RU student, and she did this work way back, well, almost a decade ago, and these were her classifications back then. We've improved on our detection experiment. We're more closer to 80% now, but roughly about 80% were detected in emission, about 10% or in absorption, and about 10% are non-detections right now. The data is quite rich, and it's quite there's a lot of information in there, more than what we were expecting necessarily to see. Some sources show high velocity components seen in this case absorption, but in some cases of emission, as well as you see multiple components of the sources. So here you have a bright, typical spiral galaxy, and then you have the neighboring source off to the side. So this will be a rich data set, and I will eventually publish this. So it will, be a lasting legacy for the sample, because the data, even though it's taken a while ago, is of very high quality. This is some of the early analysis. When we got all the H1 data together, we started to look at, the typical things. You just plot parameter X versus parameter Y and look at things. And up on the upper left, this shows the stellar masses of the sample as a function of log IR, where 12 is here and 11 is here. And the stellar masses are relatively flat. And if you look at the H1 masses, there's a lot of scatter. But if you get to the high end, you see how these drop off. And that's sort of interesting, and that's consistent with what we believe to be going on. If you plot the ratio of MH1 to stellar masses, you see it's a huge scatter here versus LIR. And that's hard to really try to figure out exactly what's going on. I flipped it around and plotting it in a different way to actually to break the population up, so you can see a jump in the data at the higher luminosities. And this is looking at the relative H1 masses plotted as a ratio of LIR over the molecular hydrogen versus LIR. And basically, and the boxes here are the medians within each data bin. There's a general increase in these points here, which is indicative of decreasing H1 mass in relative sense to its luminosity as we go higher in IR luminosity till you get up to about 10 to the 12th. And then there's a definite jump. And this would be consistent with all the H1 gas going into molecular gas and fueling the LIRG activity. And we know by studying LIRGs and CO that they're very rich in molecular gas. We don't really know how much hydrogen gas there are in a lot of those sources because they show up as an absorption, and it's difficult to measure gas masses from absorption because it only takes a little bit of gas and absorption to basically take out all the emission signal from the galaxy. But we have more data now on in molecular observations. There's quite a few different samples that have studied CO and subsets of these samples over the last, 30 years even. So I took one of the data sets from the gold sample based on the 30 meter that we had, and it was well understood, and I combined it with our early H1 observations. And then this is only a subset. We'll have more CO observations to compare with, but we'll have to try to make sure everything's on a uniform scale to make these comparisons. And this shows the mass in H1 versus the mass of molecular gas implied by the CO observations, a function of IR luminosity. And it's consistent with that previous plot in the sense that at lower IR luminosities, in this case, it looks relatively flat in terms of that ratio. But then as you get to higher IR luminosities, you have a definite transition where the sources become hydrogen deficient, neutral gas deficient, and which suggests that most of all this gas is being converted into molecular gas. In terms of our detection limits, that we're getting the median hydrogen masses in our sample is of order 8 times 10 to the 9 solar masses, which is roughly consistent about 2 Milky Way galaxies, which is consistent with 2 normal spiral galaxies merging. And our upper limits are pretty sensitive. We're an order of magnitude more sensitive than that. So this isn't a sensitivity limit issue here. There's definitely, if you go to higher luminosities, the H1 gas is deficient in them. So the conclusions aren't that dramatic in a sense, because we were expecting the sources to actually show H1 becoming H1 deficient as we move to higher luminosities and advanced stage mergers, although we haven't ever actually quantitatively measured that before. It was more hand-waving arguments. And we have the data in place to actually quantify that and look at different and compare those properties with other different properties of the sample. I would just like to say the gold samples are very diverse. Each individual source, they're their own, they tell their own story. So we tend to try to do statistical studies in astronomy, but each individual system here is actually quite interesting in their own right. So hopefully this data set will help provide people with information that they might not have otherwise to study individual sources, as well as people do the normal statistical studies and look at ratios and try to do scaling relationships to feed into the evolutionary models of galaxies in general. Late state mergers are more compact. They have higher luminosities, and at those higher luminosities of those sources, the hydrogen gas masses are basically deficient. We measure a decreasing H1 mass with increasing IR luminosity for the LIRGs populations. And at the highest luminosities, where you get into ULIRG luminosities greater than 10 to the 12, basically don't measure hardly any H1 emission. You do see it in absorption. And this is consistent with nearly all the gas being converted into molecular gas. So you have a merger of two gas systems. They fuel a lot of star formation, AGN, all the gas gets driven into the central regions, gets mostly converted into molecular gas. And that's basically the sort of the simple idea behind the data. So thank you very much. And I am open to questions here. I'm gonna stop my share, I guess. Whoops, I see questions. Or Jay, are you going to ask them?
That's okay. You can take the questions, Dave. Just let me say thanks very much. And again, to remind everyone to submit your questions through the Q&A box on the lower right.
Okay. Okay. So the first question is the IR luminosity from the LIRGs due to abundant hot dust present during high star formation rates? And does the H1 increase in galaxies at smaller Z, and I assume they mean Z meaning maybe redshift. Okay, we're not probing a very broad redshift range. It's all local from my perspective. But in general, I'm going to answer the second question first. The H1 seen in the universe basically is relatively flat over redshift based on absorption line studies over the years. And this contrasts with the molecular gas. I mean, there's a lot of evolution in the molecular gas. So that's a piece of the puzzle that is telling us something about galaxy evolution. In terms of the hot dust and ULIRGs, yes, a lot of them are pretty warm as they go up, but you can measure their masses. So yes, a lot of the luminosity, the most luminous infrared galaxies tend to be the warmest. So that is true. The dust is hot, but they still have a lot of CO and cooler dust, and they're still predominantly driven by star formation on the LIRGs. When you get the ULIRGs in the local universe, a lot of them tend to have an AGN, buried AGN in their system. Did you confirm the nature of, and another question, did you confirm the nature of those absorption features? The absorption features that we typically see is based on against the bright continuum background in the radio, so you could just see it from the host galaxy. Now that one feature that I showed in that one plot that it was at high velocity, that could be consistent with something, other cloud, or not, well, it's not only a cloud, it's massive enough, because that would have been massive enough to be an entire other foreground galaxy in the structure being absorbed, basically. So no, I haven't looked into the high velocity structures and try to correlate them, like what could be in the field that could be associated with high velocity features. The absorption features in themselves against the bright continuum I have been made. That was one of the reasons I redid all the data reduction. When I did it with the RAU student, to be honest, we were cutting a few corners and we didn't keep the continuum data. We just removed it out on baseline reduction reduction, and we didn't have the continuum information. When you see it in absorption, when you basically you measure column densities, the background source, you really don't know how much hydrogen gas is there. But you can still study kinematics, and you can see evidence for broad wings and absorption and against the bright core, as well as the gas within the galaxy and in between us and the bright continuum source. But I think there are a lot of, when we publish the data, I'm not going to write all these papers. There'll be a lot of little stories one can tell. People will have their favorite galaxy and they'll pull that out and they'll look at it and see different features and correlate it with other components within the galaxies and components of multiple galaxies. Because in some of these systems are in like local groups of galaxies. So there's a lot of stuff going on. So the LIRGs and LIRGs by themselves are sort of a signpost of major merger activity between two galaxies, but in some cases there's like other smaller galaxies in the system that are all also interacting with the ongoing merger event.
Okay, thanks, Dave. Any more questions? We have time for one or two more. Oh, wait, here comes one in.
Can you classify any of your systems as pre versus post maximum star formation activity, pre or post? Well, maximum. The LIRGs, most of them would be pre of the LIRGs they haven't completely coalesced yet. Of the highest luminosity ones, ARC 220, for example, or the ultraluminous galaxies, we're close to maximum, basically. So most of them would be pre-star forming activity. I don't think we have any LIRGs that look like post, because if they're post maximum starburst, they decay pretty quickly. They've consumed their gas. They wouldn't show up in the IRAS sample. So this is sort of a selection effect. So we're picking the sources that are ramping up in IR luminosity to their maximum IR luminosities. And then after the gas is consumed and or blown out, so to speak, the IR luminosity would drop like a rock and we wouldn't see them. So the selection effect of picking out bright IRAS sources basically means most of these sources are approaching near their maximum IR luminosity, but they're still in the very active stage.
Okay, thanks very much, Dave. Thanks again, and I'd like to thank everyone for attending and remind you that these sessions are recorded and within a few days of their will be available on our website. And you can go to the greenbankobservatory.org to look at a list of past talks that you can then view. And we'll return in 2 weeks on October 27th, where Amanda Kepley of NRAO will be describing the dense molecular fueling of star formation in nearby galaxies. Thank you, and we hope to see you then.